Hey Algebra 2, in this video we're going to be starting chapter 6 and we're going to start with key features of exponential functions. We've learned many functions this year. Exponential's a little bit different. Let's talk about the parent first. So remember, every function has a parent function. The exponential parent is interesting and unique because there are actually many of them. I guess an infinite amount. There are many parents. Because the base can change. So we'll do an example of a parent real quick. An example of a parent would be y equals 2 to the power of x. So this is an example of a parent. Parent of an exponential function. So our table will always have the same x values. So we'll do -1, 0, and +1. So always the key x values. Y values are going to change depending on the parent. So for this one, we're going to substitute -1 in for x, and you get 1/2, right? Because anything to the -1 power we can write as the reciprocal. 2 to the 0 power is 1, and 2 to the first power is 2. Now let's make our coordinate plane to graph. I'm going to go up to 3. And then my x values, I'm going to go to 3 as well, 3 and -3 I suppose. Okay, so to plot it, we've got -1, 1/2. We have 0, 1, and 1, 2. You'll notice it's making a curve. You actually learned about this back in Algebra 1. So curves up, and then just like what are the other functions we did? The rational function. We have an asymptote at y equals 0. So the exponential function has a horizontal asymptote. Yeah, so this is an example of parent. This parent is representing an exponential growth because the base is 2. If the base is a fraction, for example, y equals 1/2 to the power of x, right? Then it represents exponential decay. So if the base is a fraction, you will have decay. If the base is a whole number, you will have growth. Okay, so the generalized equation is y equals a times b to the power of x, and b is equal to the base. With every single transformation, it would look like this. Y equals I'm going to use numbers for this because I think it makes it easier. So if I have -2 and then in parentheses 4 to the power of, in parentheses, -3 times x plus 1 and then -5. Okay, so a lot going on here. First of all, the parent is important. Right, so what is the parent of this function? For the parent, you need to look at the base, right? It depends on the base. Like Meghan Trainor says, it's all about the base. So the parent here is y equals 4 to the power of x because the base is 4. And this will be a growth. Reflections. Okay, so this reflection, do some color coding. This negative, right, anytime you're multiplying by a negative, you'll have a reflection. The one that I've highlighted in blue is a reflection over the x-axis. Okay, whereas up here we're multiplying by another negative number. So that's a reflection over the y-axis. Here's my green pen. Okay, reflect over the y-axis. So this negative is reflect over the y-axis. Okay. Okay, so those are reflections. Now let's talk dilations. Alright, so dilations are also going to multiply just like they have been for any other function. So here we're multiplying by 2 to the base. And that's going to be a vertical dilation by 2. And here we're multiplying by 3. That's going to be a horizontal dilation by 1/3. Remember, it's still going to be the reciprocal. Okay, now we just have translations. And when it is on the outside like this, we are translating down 5. But then when it's affecting the x values, we are translating not right, but left, because it's the opposite. Okay, so a couple things I'd like to point out real quick. Translations are applying just like they have for every other function we've talked about, for quadratic, for absolute value, for square root, for rational. Anything with the x value is happening, affecting your x's is happening like the opposite of what you would think, right? So when we multiply by 3 up here in the exponent with x values, that's a horizontal dilation by 1/3. With the x, we're adding 1, so it's going left, right? So it's the opposite of what you think. It's important to keep the dilation factored out, because if it were multiplied in, you'd have to, this is still being translated left 1. Anything down below is affecting your x values. Is affecting your y values. So reflection over the x-axis, vertical dilation by 2, translating down 5. Now here's what you're going to mess up, the base. You're going to forget that there is a base, and that's what's unique about the exponential function, is the base. So, and we'll talk more about that in the future, but this is not a transformation. You have to be very careful. So that's why I recommend always identifying your parent first, so that you realize that that is the base of the parent, that is not a transformation. Now, remember with our parent function, we had an asymptote. We have a horizontal asymptote at y equals 0. So what is going to affect the horizontal asymptote? Hopefully you have an idea, but it's going to be a vertical translation. So a vertical translation will change your asymptote. And that's really similar to the rational functions that we had, right? Translating up or down always moves your horizontal asymptote. And we only have a horizontal asymptote for this function, so it makes sense.